Hello everyone. Today we are presenting the Smart Hybrid Pulse Power Electrochemical Manufacturing Machine. The purpose of our project was to utilize two similar yet separate processes. The first one is electrochemical additive manufacturing, or ECAM, which is an alternative method of metal printing that uses electrolysis or the use of electricity to drive a chemical reaction. This would allow for localized deposits of metal onto a build plate to create micro and nanostructures, which is applicable to certain industries like medical industry, electronics, and aerospace. The second process is called electrochemical machining, or ECM. This removes material through a similar process to ECAM. The only difference is that you reverse the polarity of the power supply, allowing the tool to become the cathode and the build plate to become the anode. The removed material is resolved into the electrolyte, and this process happens at room temperature. Since the tool never makes physical contact with the part tool wear is non-existent, and the rate at which material is removed is dependent on many factors like the voltage, current, and tool gap from the part.
So to move our system around, we needed a precision movement system. We did high precision ball screws that rode on linear rails. Those were driven by 0.9-degree stepper motors for very fine movement. Those were then connected to planetary gearboxes for even further reduction. This allowed us to have a 1 micron step size, with the total system having plus or minus 10 micron precision. For our container, the electrolyte that contains our dissolved metal is highly corrosive. So we used acrylic so we could have it be clear to see inside and handle the corrosive. And then we had 2 O-rings on the bottom for redundancy to ensure that the electrolyte never leaks outside of the build container.
This PCB is the pulsing power supply used to control both the electrochemical machining and additive manufacturing processes. Its main purpose is to generate high-speed voltage pulses between the tool and workpiece while also measuring the current during operation. By adjusting the pulse frequency, duty cycle, and voltage, we can control how much electrical energy is delivered to the machining gap and improve the precision of material deposition or machining. The board is divided into 2 main electrical domains. The logic and control domain receives the PWM communication signals from the microcontroller. The power switching domain contains the isolated gate driver, MOSFET, current sensing circuit, and the connections to the tool and workpiece. Separating these domains helps protect the control electronics from electrical noise and voltage transients produced by the high-speed switching. We produced 2 revisions of the PCB. The first revision could pulse up to 10 megahertz, but the maximum short current was only around 300 to 500 milliamps at 5 volts, and we could not read the current at all. The second revision maintained the 10 megahertz capability, added working current measurement, and increased the short circuit capability to over 2 amps at 5 volts. The main improvements were larger switching traces, terminal blocks, and a low dropout regulator to provide a cleaner, isolated 5-volt rail. The pulsing power supply PCB had 3 main connections. First, a 24-volt constant power supply powered the PCB and all its components. Next, an adjustable DC power supply, which allowed the user to adjust the amplitude of the pulse. And finally, an interchangeable anode and cathode pair for ECAM and ECM modes. The PCB also had header pins, which allowed it to interface with the STM32. The STM32 provided a PWM signal for the PCB, and it sampled the current measurement while communicating to the PCB via SPI. The STM also connected to the Raspberry Pi through a USB to UART, where it could send the current data and receive user inputs for changing the PWM pulse.
All right, the power supply that drives the pulse power supply also drives our motor control board. For this project, the Octopus version 1.1 was chosen for its ability to run G-code through softwares such as Clipper and user interface called Mainsail. The board operates as 3-axis motors, the linear stage limit switches for each axis, and 2 fans cool the electronics housing. From there, it communicates with the Raspberry Pi, which is utilized as a central computer for the user interface with mainsail and handles communicating to and from all the other devices for user settings of control, current feedback, and motion control.
Our main interface is called Mainsail. It is a powerful open source web interface for the Clipper 3D printer firmware. It allows us to configure electronics such as stepper motors, end stops, and fans, write macros, and upload and run G-code. Our interface also includes project-specific controls for the STM, the CoRad power supply, and the live current reading from the print. We have 3 Python programs that help us run these systems. The CoRad bridge runs constantly on the Raspberry Pi and connects the CoRad DC power supply over USB, allowing us to set voltage, current, and output state from mainsail. ECAM Cleaner is a Flask web app that prepares and configures G-code for our specific machine. ECAM Bridge handles the automatic Z-axis gap correction, communicates with the STM, programs the pulse characteristics, and reads the current. The STM microcontroller is our last main controls group. It receives commands from mainsail through the Raspberry Pi over the USB to UART line. It generates pulse width modulation based on those commands and receives current measurements from the PCB through a 3-wire SPI connection. The STM then sends the current data back to the Raspberry Pi, where ECAM Bridge decodes it and makes it available to mainsail.
For our ECM testing, we tested hole drilling at different frequencies and different duty cycles. We found that lower frequencies had less precision in a wider affected area, while higher frequencies had more precision. For a duty cycle, a lower duty cycle had more precision, but much longer run times, while a higher duty cycle had less precision, but a lot shorter run times. For our ECAM testing, we tested a 7 model, which allowed us to demonstrate our ability to print in thin air without support materials, as well as a spiral test, which was a continuous upward movement, which allowed us to control the gap all the way as we went up, which gave us very good results. Special thank you to Dr. Kamaraj for his insight into the ECAM and ECM parameters, Dr. Rakora for his help with the PCB, and Dr. Naruzi, Krug, and Olkai for their advising throughout the semester.